When can we use a line to make a prediction for a data set? To answer this question, we will first look at scatter plots. A scatter plot shows the relationship between two sets of data. This picture illustrates the relationship between a final exam score and a third exam score. The third exam scores are your X's, and the final exam scores are your Y's. The X value is always your independent variable, and the Y value is always your dependent variable. For this example, your independent or explanatory variable is the third exam score, and the dependent or response variable is your final exam score. Your scatter plot can help you determine your shape, strength, and trend. The shape is the pattern that you see in your data set. So, for example, if the data has a line pattern, then it has a line shape. Now, there's other shapes out there. It could have a exponential pattern, so it would have a exponential shape. It could have a parabolic pattern, so then it would have a parabolic or a parabola shape to it. We also want to look at the strength of the pattern. Does it have a strong line pattern, or does it have a weak line pattern? That's one question we could ask. This fact can help us determine if it's appropriate to use a line to approximate the relationship. The trend tells us the direction. We can look at the trend for scatter plots with a line or exponential pattern. Something else that's also important to consider is the linear correlation coefficient R. The linear correlation coefficient R measures the strength of the linear correlation between the variables and is a value between -1 and 1. The closer R is to 0, the weaker the linear relationship will be. If R is very close to 0, then a data set will not have a linear relationship. So again, if it's really close to 0, it's not really going to have a linear relationship there. The closer R is to -1 or 1, the stronger the linear relationship will be. Let's take a look at some examples of scatter plots. Again, the big question that we're trying to answer is, when can we use a line to make a prediction? Another way of thinking about this is, when would it be appropriate to use a line to approximate the relationship? So when would it be appropriate to use a line to approximate that relationship? Well, we can only do that when the scatter plot has a line pattern. If the scatter plot does not have a line pattern, then it doesn't really make sense to use a line to approximate that relationship or to use a line to make a prediction. So that's the first thing we're really going to look for, is, does the data set have a line pattern? Now let's look at scatter plots 1 and 2. Scatter plots 1 and 2 both have a line pattern to it. So that part's good. The next thing we want to consider is the strength of the linear correlation. Now, if we're looking at scatter plots 1 and 2, scatter plot 1 is going to have a stronger linear relationship than scatter plot 2. And you may be wondering why. Well, it's because scatterplot 2 has this outlier. This outlier is going to cause it to have a weaker linear relationship. And this is illustrated with the R values. If you look at the R's, your R value for scatterplot 1 is going to be really close to 1, making it have, well, that tells us that it has a very strong linear relationship. Whereas in scatterplot 2, my R is getting closer to 0. Now, this is still a pretty nice R value, but still it's going to be weaker in terms of its linear relationship than scatterplot 1. So the closer that your R value gets to 0, the weaker that linear relationship will be. Now, something else we can look at is the trend. Both of these are moving in the positive direction, so they have a positive trend. And you should also notice that these R values are positive as well. That matches up with your trend. Let's look at scatterplots 3 and 4. Both of these have a line pattern to them. Now, 3 has a nicer line pattern, though, than 4. In 4, the data values are pretty spread out. So we would say this one has a weaker linear relationship. And again, that's also reflected in our R's. Scatterplot 3 has a really nice R value. It's close to -1. Whereas in scatterplot 4, this R value is getting closer to 0. Now, with the R value that it has, we can't definitively say whether it has linear correlation or not. This is a situation where we're going to have to do more testing. In particular, we're going to have to run a formal hypothesis test to determine if it has linear correlation or not. And I have a general rule for you to kind of help you determine that up here in these important notes. So if your R is between -0.4 and 0.4, we want to conduct a formal hypothesis test for linear correlation. So this is when we're getting into the territory where it's a little bit iffy. We don't know for sure if there's linear correlation, but they could be linear correlations there. So we want to test when we have R values, again, between -0.4 and 0.4. So that would be a situation like scatterplot 4. Now, both of these R's are negative. So what do you think that's going to tell us about our trend? Well, it's going to cause us to have a negative trend, and that's also represented in the scatter plot. If you look at these scatter plots, they're both moving in the negative direction. So it tells us our trend is negative. Okay, now let's look at scatter plots 5 and 6. For scatter plot 5, this one does not have a line pattern. It actually has an exponential pattern. Since it has an exponential pattern, we wouldn't want to use a line to approximate that relationship. In this case, we would actually want to use an exponential function to approximate it, but we're not really looking at those. We really just want to know if we can use a line to approximate it. So for this one, we wouldn't. We also would not do it for 6 because the pattern is unknown. I mean, if you look at these data values here, it's very hard to try to see a pattern in the scatter plot. So this is another situation where we would not use a line to approximate that relationship. And you can also look at the R value for 6. If you notice that R value is really close to 0, which again is telling us that there is a very good chance for no linear correlation. The next thing we're going to look at is line of best fit, or the regression line. The main reason we was looking at scatter plots was to determine whether or not it would make sense to use a line to approximate that linear relationship. So let's go back and look at this first example here. We were looking at final exam scores and third exam scores in the scatter plot. Could we use a line to approximate this relationship? Or in other words, does this scatter plot have a line pattern to it? A strong or at least moderately strong line pattern to it? And the answer would be yes. This actually has a line pattern and it's got a pretty nice line pattern to it. So we would think it would make sense to use a line to approximate it. Now the next question would be, what would that line be? How could we find it? So the line that would approximate this relationship is called our line of best fit or a regression line. The goal of the line of best fit or regression line is to have a line that is close as possible to all points. So all points in your data set. The regression line minimizes the vertical distance between the data values and the regression line. Now this is your regression line here. Your A is your Y-intercept and your B is going to be your slope. To find this regression line, you're going to be using technology to get it, either a calculator or Excel. If we determine the line of best fit for this scatter plot, it's going to be this blue line here. So this would be our line of best fit. And again, we find that using technology. Of best fit. And this line of best fit is going to help us make predictions. So let's talk a little more about the line of best fit before we go on to making predictions, because there's a couple things we want to look at in terms of our line. It's always good to interpret your slope and your y-intercept. So if I'm looking at this example here, how would we interpret our y-intercept? Well, for this one, the y-intercept is the final exam score when the third exam score is 0. That would be my y-intercept. My slope is the change in the final exam score over every unit increase in the third exam score. So again, it's always good to interpret your y-intercept and your slope. Okay, now let's get into making predictions. So when we're trying to make predictions, it's always good to identify your scope. So your scope is just basically your initial range for that data set. So it would be going from here to here if you're thinking of your scope. Okay. Anytime that you predict inside your scope, you're going to be good, at least when we know that we can use a line to approximate that relationship. Then we're going to be using that line to make a prediction inside that scope. And we can do that just fine. There's not going to be any problems. Now, anytime we go outside the scope, this is called extrapolating. And when you extrapolate, sometimes you can run into problems. So I just want to caution you on that. If you predict too far outside your scope, you may be getting misleading results. And you may be wondering, well, how can that happen? Let me just show you an example. Let's say we had a scatter plot and it looks something like this. Let me put it on here. There we go. And it looks something like this. So if we look at this scatter plot, let's say these are the data values I have so far. This one has a very nice line pattern to it. It would definitely make sense to use a line to approximate that relationship, and we'd be able to find that regression line to make predictions. Now, let's say we wanted to predict pretty far off in the future. So let's say we're wanting to predict for something all the way out here. Again, if you're using this line for prediction, you could technically do that. You could, predict all the way out here, but you don't really know the behavior of this data set, after your last data value there. It could completely change behavior. So let's say it does. So let's say it completely changes behavior after this data point here. Maybe instead of a line pattern, let's say it suddenly turns into like an exponential. So it could look something like this. Make it look a little nicer. And it's got kind of an exponential shape there. So let's say it changes behavior and looks something like this. But it still makes sense to use this line to approximate that relationship. Well, the answer is no. Right? This wouldn't be a good way to model the data set at this, for these particular data values here. So this is a situation where we would get in trouble if we use that line to predict too far into the future. So just be careful of that. Anytime that you're extrapolating, you never know the behavior of your data set, and it could completely change, what you're looking like. Maybe with the original data values you were looking at, it was something you could approximate very nicely with a line. But then let's say you looked at more data values and all of a sudden you get an exponential look to it. That would change, how you predict values. So just be careful. Don't go too far in the future. You can get, in trouble if you do that. But as long as you're predicting inside your scope, you'll be good. So let's do that. Let's actually make a prediction, and let's do it inside the scope, so we'll be okay there. So again, we're looking at the same example, final exam scores, third exam scores. And let's say that we want to find the expected final exam score when our third exam score is a 68. That's something we can definitely do. So how could we determine that? Again, we're going to use this line to make a prediction. So how will we do that? Well, we could go here to where 68 would be. It'd be right here. And we can see where that hits on the line. And put a point there. And we can determine the corresponding Y value. That corresponding Y value will be my predicted value. Okay, again, we're using this line to make a prediction. Or if we have the line of best fit, which is right here, again, I found this using some kind of technology. How could I make that prediction? Well, all I'd have to do is replace my X with 68. So again, I'm plugging in 68 for X. And then I'm calculating this. When I calculate it, I'm going to get 154.93, and that would be my predicted final exam score.